you see my slides?
Yes, we see your slides, yes.
Perfect, thank you. So thank you very much for the gentle introduction. My name is Guglielmo Frido. As Hugo mentioned, I joined METAS less than 1 year ago in June 2020. And today I would like to present you which are the main challenges from the measurement point of view for the new smart grids that will be the new way of conveying and consuming electricity for us in this ever-changing society. So my presentation is divided in 3 main blocks. First, I will present what we mean when we talk about smart grid. Then I will present what is the role of measurement in this new scenario. And finally, I will briefly introduce one of the applications we have here in our electrical energy and power lab of METAS that is directly linked with this new emerging technology that is smart grid. So let's start by introducing what is a power system. So electricity has become one of the critical infrastructure of modern society because we use electricity in all the aspects of our life. And the electrical power system is a very complicated infrastructure that consists of all the components, devices, and controls that we deploy in order to supply, transfer, and use the electric power. Since the last years of the 19th centuries, when it was first founded, power system has been always organized as a very strictly hierarchical structure, where we go from the generation, so the power plants, downwards up to the end consumers, like me here in the office with the plugs. And why it is important? Because in this traditional conception of power system, the electricity flows in one single direction from the power plant downwards to the end user. And for the sake of optimizing the convey of energy, the grid, the power system is divided into several grid levels, each one characterized by different voltage levels. So we have very high voltage at the transmission grid, where the electricity is generated. And then by means of transformers, the voltage level is transformed and reduced up to the 230 volt we can find at the plugs of our offices and our houses. So this is a very easy and simple structure. And as you can see, it's quite also linear to control all this flow of energy because we have only one generation and all the demand on the other side. Now, we live in a very peculiar condition because Europe, because of how it evolved during history and because of the amount of population that lives in Europe, is the largest synchronous area in the world. This means that the power system in Europe is all interconnected and is organized as a very meshed and dense grid. So all the countries are connected one with each other, and we all share the same system frequency. So electricity in all Europe is provided at 50 hertz, whereas, for instance, in the US is 60 hertz. Europe is the biggest market for energy because we serve more than 400 million customers, and we are able to generate more than 650 gigawatt. Why it's important to live in such an interconnected world? Because this allows for minimizing the cost of generation, for keeping the market of energy open, and so lowering the price, and also for mutual assistance, because obviously we can sell or borrow the energy to a neighbor country, or we can import energy from a neighbor country. On the other hand, to live in such a meshed grid produce a little disadvantage. So wherever there is a problem in the network, the effects of this problem will be evident not only in the country where the problem occurs, but all over the network. A very simple example happened in December 2016, when a transmission line between France and Spain opened because of a fault, and this produced an oscillation of the entire network from Portugal to Turkey, because all the other countries tried to balance the absence of this connection, so tried to send energy towards France, Spain, and Portugal. And this created a kind of oscillation in all the system. And if we look in those moments at the frequency measured in all the countries of Europe, we can see that we pass before the contingency, before the fault. All the countries are more or less at 50 hertz, but when the contingency occurs, not only Spain and France, that are the two countries involved by the problem, starts to oscillate for many, many seconds, for minutes. In this graph, the time scale is 10 seconds per division, so it's quite long. But also neighboring countries like Germany, or very far countries like Denmark and Turkey. Turkey is exactly on the opposite side of the network, observed very large deviation of the frequency. So this means that when an event happens all over Europe, all the continent will face the consequences of the events. So we have to keep the system the more stable possible. Why it's important, this description, for us that we live in Switzerland? Because Switzerland geographically is the central point of the European grid. And so it serves two major roles. First of all, Switzerland is the interconnection between the north-south and the east-west connection. And so all the energy that is flowing between Europe passes through Switzerland. And the other aspect is that Switzerland has many pumped storage plants, so it can store the energy that is produced in excess. And so it's a sort of energy storage facility of the continent. So Switzerland has not only an important role in terms of control, but it's really a strategical place for the entire electrical strategy of Europe. Now, at the end, as end users, what we are interested in? We are interested to have a service that is continuous and stable. So not to face any problem when we plug in our computer, our phone, and so on. In order to keep this stability, we need to measure and track three main parameters. So this is a typical three-phase plug that you can find in our labs. And at the terminals of this plug, what we expect to see is a three-phase sinusoidal signal, where each phase is shifted with respect to the others by 120 degrees. Since we are talking about sinusoids, the parameters to fully characterize a sinusoid are the magnitude, the frequency, and the phase angle. Each of these parameters accounts for some information about the state of the system. The frequency tells us how stable is the grid. The magnitude will tell us if there is a disturbance or an event occurring in that specific moment. And the phase angle guarantees the balance between the three phases, and so the optimal transportation of energy. But in particular today, we will focus on frequency and on its first time derivative that in electrical energy is called rate of change of frequency, or briefly ROCOF. Why we focus mainly on these two parameters? Because these two parameters are indicators of the balance between the supply of energy, so our generation facilities, and the demand. We want always to keep this balance as stable as possible. And as you can see from this little graph, if we generate too much, the frequency will start to decrease. And if the demand is too much, the frequency will the opposite. If we generate too much, the frequency will start to increase. And if the demand is excessive, the frequency will start to decrease. it's a very simple balance, but the system, especially here in Europe, is very, very unstable. So we have to be extremely careful and keep, as far as possible, the frequency always around its nominal value, that is 50 hertz. How can we do it? So it's difficult to set the demand because the demand depends on the users, and the best way to control the demand is by using marketing policies, so by changing the cost of energy. Instead, it's easier to control the supply because it's the generation, so we have a direct control on it, and we have to try to continuously tune our generation based on the demand we have. At the beginning of this year, the 8th of January, another event happened, and the event that happened in the Balkanic area was due exactly by an improper management of the balance between supply and demand. And the system in some parts of the Balkanic area had a kind of blackout. So what are the regulations in Europe? In Europe, there exist many regulatory offices that have set some rules that are valid all over the continent. And they have set some very strict requirements. Just for our understanding, frequency shall never exceed a range of plus minus 2.5 hertz per second, 2.5 hertz with respect to its nominal value. This means that frequency shall never exceed 47.5 hertz or 52.5 hertz. If this happens, the system trips and we are in blackout. A similar condition is put on the frequency derivative that has to be limited at no more than plus minus 2 hertz per second. So these are two very strict limits. If we cross these limits, we go in blackout, and the operators of energy will have very, very high economical fees from the European Union and the regulatory offices. So these are limits that are always enforced in all European countries. But how are we able to keep balance in such a time dynamic world like the market of energy? So in a traditional power system, this is the map of Switzerland. Each star represents a power plant. So as you can see, Switzerland has many power plants distributed all over its territory. And all these power plants can be seen from a physical point of view as rotating machines. So we have these big engines that are all rotating with the same speed. In this kind of situation, it's quite easy to keep the balance because it's like to have a car that is running at a certain speed on a straight road. And if nothing happens without accidents, this can continue almost forever. And why? Because these big power plants, these big rotating machines, have, as any other rotating mass, some inertia. So what is inertia in power system? As our power plants are rotating with a certain speed, if I need to increase the speed of my generator or to decrease the speed of my generator, so to increase or decrease the generation rate, my rotating mass cannot change its speed immediately. It will take some time to reach the desired level, the desired speed, because a big rotating mass cannot be accelerated instantaneously and at the same time decelerated instantaneously. To give just an easier example to understand, let's imagine to be on a bicycle. If we want to go downhill, we don't need to pedal because the energy we have will be sufficient and the bike will continue to run even if we don't pedal. So when we want to decrease our speed, we can, yes, stop pedaling, but the bike will continue and will slow down very slowly. At the same time, if we want to do the opposite, so if we want to increase our speed, but we are going uphill, we have to put a higher effort because there is a kind of force dragging us and so going against us. So inertia in one case and in the other case is a kind of dampening factor that is slowing down the system response. This can be seen as a disadvantage when we want to change and vary the situation very fast. But in most of the cases, it's a big advantage because it gives to the control room, to all the people that is managing the network, the time to analyze the situation and take the best control action. So no need to take instantaneous control, but we have time to react. But why to change this system? So if it's so stable, if it's so reliable, why do we want to change our power system? Because the society is growing an environmental soul, so we have more concerns about the conservation of this planet, and we know that how we generate energy at the moment is not a viable and sustainable solution. In Switzerland, the Federal Council, almost 10 years ago, launched the Energy Strategy 2050 that aims at reducing the consumption of energy and promoting the integration of more and more renewables in our network. The idea is to arrive in 2050 at the complete withdrawal of nuclear energy and to pass to a power system that relies mostly on renewable or green source of energy. Is it doable? In principle, yes, because Switzerland can benefit from a huge variety of renewable energy sources. Here I'm showing 4 possible solutions like wind power plants, hydro, solar, and the biomass. So we have many generation facilities and we can obviously enlarge all these options. But the other big advantage is that before, when I was showing the traditional power system organization, the generation was only at the transmission level, at the very left of our scheme. Now, with the renewables, we can integrate generation at any level of the network, at any voltage level. So this would allow to plug in possible energy sources everywhere, here at the METAS, at home, wherever. Why? Because the connection does not require specific cables, specific transformers. It's just an inverter that is based on power electronics that is able to convert a DC, a continuous current, in an AC current, alternating current. This is the main concept of smart grid. Why smart? Because now we can produce energy wherever we want and distribute it no more in a single direction, but wherever it's needed. So the big change is that in the traditional power system, wherever energy is needed, we have to complete the path from the large-scale generation up to where the energy is needed. In the new paradigm of smart grid, we can generate the energy very close to where it's needed. And the advantage is that we will have less line congestion. So we will not have a line of energy that supplies all the Zurich industrial area that will be super congested because there is a very high need for energy there. So there will be a more distributed and better organized generation. But unfortunately, there are also the disadvantages. So renewables have no direct control. We cannot control them directly because they are based on natural and physical phenomena that are not fully controllable by man, differently from thermal power station where we burn some material, so we do know what we are producing. And this new generation has less inertia. Before I presented you all the generators as rotating machines that take some time to change their speed. Instead, all these new renewable energy sources are connected just through power electronics. In this case, any variation is immediate. There is no time to respond. And as we do not control the wind or the sun, we are not able to tune our generation based on the actual demand of energy. This can cause some problems and unfortunate events. The most famous in the recent years is the blackout that involved South Australia in September 2016. So in September 2016, before an unfortunate event occurred, the generation of the Adelaide area was by almost 50% relying on wind power plants. But unfortunately, a very big storm with winds over 100 kilometers per hour arrived, and the wind power plants had to stop because of safety reasons. Otherwise, the wheel turns too fast and can produce some mechanical problems. The wind was so strong that some transmission lines, some transmission tower were taken down. And so we had many faults, 3 transmission lines opened, and in 1.5 minutes, we arrived at the blackout. And if we look at the frequency in the Adelaide area, we can see that we were quite stable. And then when the event occurred, this kind of snowball effect of problems concatenating to other problems produced a huge drop of the frequency that was going down by minus 6.25 hertz per second. If you remember, before I said rock-off should never exceed plus minus 2 hertz per second. Here we are more than 3 times. And as soon as we will reach 47.5, there will be blackout. And in fact, an entire part of Australia went in blackout. This is not to blame renewables, but this was a very complicated configuration and a very unfortunate combination of events. And if we look at the specific example of South Australia, the region of Adelaide is not like in Europe connected to all the rest of Australia because of the geographical configuration of Australia. So we have only 1, 2, and 3 big connections with the rest of the country. Once one of these connections is lost, and once you lose all your wind generation, so 50% of your supply, there is no way to avoid the blackout. So the take-it-home lesson is renewables are a very promising solution for making the grid greener, but they cannot be accounted as an emergency reserve. So if there is an emergency, renewables cannot be our solution. The other big problem is that before we were working in a quite stable condition. If you remember in the first slide about the oscillation in Europe, I showed you the system frequency oscillating, but most of the cases we are around 50 hertz. And if I look at the spectrum of my power signal, I will see that most of the energy is transmitted around 50 hertz. And when we deal with these signals, we know very well how to determine the amplitude, frequency, and phase of a sinusoid. But during a dramatic event like South Australia, we will deal with a continuous spectrum where just 1/3 of the energy is around 50 hertz. And it's also mathematically challenging to define what is frequency when the spectrum as this particular shape. And this is very challenging because the metering system has to give us this information to take the most appropriate control actions. So we have to work to be able to fully characterize not only the nominal conditions, but also the most challenging and dynamic condition. So what's the most reliable solution from the technological point of view? The best idea at the moment is not to inject directly the renewable energy sources in the grid, but to store their energy in some big batteries, because the batteries will be able to dispatch almost immediately the energy, so we can keep the energy in the battery and dispatch it, make it available only when needed. And so even if we don't have inertia in a wind power plant, we can have a kind of synthetic inertia just by putting the energy in the battery and then supplying only when needed. So this is, at the moment, the best idea to deal with renewables. But it's clear that we cannot deploy this infrastructure on our Bern and Wabern grid without doing some experiments before. So at the moment, we are just at the level of doing some tests on what we call microgrids, so very small grids where we can do some tests without the risk of affecting important facilities like hospitals, industries, and so on. Here in Switzerland, one of the most important example is the EPFL microgrid. So the campus where I was before, you can see the Rolex Center for the people who knows EPFL, has 5 buildings that are connected together. In these 5 buildings, they have installed some solar panels. There is a big battery energy storage system, and they try to make this part of the campus to operate in islanded mode, so disconnected from the grid of Lausanne. And they test whether it's possible to use just the solar panels to supply the offices. So they do some crash test to see how good is a purely renewable grid. And obviously, if the test fails, they can reconnect to the grid of the campus and we can continue. An even bigger test bench that has been used also in many European projects like Rockoff or Microgrid project is a small island that is Danish, but it's placed just below Sweden, and it's called Bornholm Island. It's a very little and almost deserted island where only a little group of fishermen lives. So the idea of the Danish government is to deploy as many wind power plants as possible in the island and do some tests to try to let the island continue and live just with the wind. Obviously, this produces many unfortunate events, but the community is so small that the economical repercussion is limited. Once with this test, we will be able to guarantee a decent stability. Probably we will be able to deploy also in our normal cities this kind of solutions. So at the end of this presentation of what is a smart grid, we have 3 main challenges. Are we able to measure frequency and drop-off with sufficient accuracy, especially when the signal is not a simple steady-state sinusoid? Are we able to give our measurement in a timely way, because we have seen that few seconds are enough to end up in a blackout? And are we able to find a way to keep the interoperability and comparability of the measurements taken in different points of the network? This is what is required from measurement guys, so for us in the meteorological institutes. In the new smart grid scenario, the measurement infrastructure is like the backbone of the control strategy. So the idea is to have networks like this, a medium voltage distribution network, where we deploy solar panels, electric vehicles, wind, and whatever. And we need to create a kind of distributed sensor networks where we place the meters at specific points of the network to guarantee observability. All the measurements are gathered by the control room, and the control room will take the most suitable control actions to keep the balance. This is the idea on a small area, but this can be reproduced on a very large scale on the entire continent, and it's more or less what is done at the moment. So Europe is organized as a huge sensor network that provides a wide area monitoring system that guarantees a situational awareness in normal and abnormal conditions. So the idea is that in all the transmission system operators of Europe, they have control of the meters placed also in the other countries, and they can have a big picture of what is going on. Similarly to what I presented for the inter-area oscillation before, here I'm showing that we have meters placed in Portugal, Turkey, Slovenia, Austria, Italy, wherever, also here in Switzerland for Swiss Grid. And we can continuously control how the situation is in each country and take appropriate control actions to keep the balance. Here the scale is quite small, but I can tell you that the frequency is varying by 50.02 to 49.94. So we are talking about 80 milliards over 1 minute. So these are very, very small variation, even if the distances between the points we are measuring are thousands of kilometers. Okay, why do we want to monitor several nodes of the network? Because this, yes, can give us the possibility to monitor the state of the network, but there are many other applications that we will be able to offer if we have a very good distributed sensor network. First of all, this is the example again of the EPFL microgrid. Once we know the voltage and current in some of the nodes of the network, by means of system identification techniques, we can know the voltage and current in all the other nodes of the campus. We can know how the power is flowing from the solar panels to the rest of the campus, from the battery to the rest of the campus. We can make an online rating of the lines to understand if some lines are congested or not. And based on this measurement, we can decide whether to deploy the energy in the battery or not. So this measurement infrastructure is crucial if we want really to use in an effective way renewables. But first of all, we have to change really the technology of the network. So we have to bridge a technological gap. If we look at the substation we can see all over Switzerland, the oldest one are still based on a lot of cabling. Very, very long cables, and each line has a specific switch, a specific control. And this is obviously not effective because then if you have to take a control action, you will decide locally each line per line. So this does not work. The idea is to pass to a more digital and optimized control where the information is first merged locally and then transmitted via specific communication protocols at the regional area and then at the central area, national area, and over national area. So this aggregation of information will enable us to take more optimized controls that will not affect the entire Europe, but maybe just the municipality of Bern, maybe just the canton of Bern, without affecting all the nation just because of a single fault. So this is the first big economical investment that the country has to do if we want really to deploy our measurement infrastructure and to use it effectively. But at the end, what these meters have to measure, as I said before, we will deal with sinusoids, so amplitude, frequency, and phase. But this is a way that is quite complicated and difficult to compress the information over the line. So electrical engineers have produced some models to better compress this information. The first model was introduced by Steinmetz that decided to represent the state of the electrical energy by means of a complex quantity. So by just applying the Euler formula, he decided that you can associate to the sinusoidal signal just the complex phasor that is rotating in the plane. And the most important advantage of this model is that this rotation corresponds to the rotation of the rotating machine in the generators. So this gives also an idea of how the system is going on. But this system has no interoperability between different measurements. So almost 1 century after, so at the end of 20th century, 2 professors at Virginia Tech, Fabke and Thorpe, proposed to take and transmit the phasors only in correspondence of the occurrence of an absolute time reference, provided, for instance, by GPS or PTP. So in this case, we pass to consider the phasor of Steinmetz, not all over the time, but just at specific time instants. And this new mathematical model is known as synchrophasor, because it's a phasor that is synchronized to an absolute time reference. Why the synchronization? Because if we are sure to observe the phasors at different nodes of the network at the same time, we are sure we can compare comparable quantities. So we are sure that the phase we are observing in Portugal is comparable with the phase we see in Turkey, in Slovenia, and so on. And once we know what we want to measure, obviously we need the instrument. So the need for measuring synchrophasors has pushed the design of a new typology of instrument that is called phasor measurement unit, or with the acronym PMU. The first PMU was done in 1992, and at the end is just an ADC with a low-pass anti-aliasing filter that converts the voltage and current three-phase signals, made some computation to extrapolate the synchrophasor, and then outputs on the Ethernet the voltage synchrophasor, the current synchrophasor, and the associated timestamp logged to GPS or PTP. If we look better at how it's done internally at PMU, as I said, it's quite an easy instrument. So we have the analog to digital conversion. Then we demodulate the signal by means of a quadrature oscillator around the nominal system frequency, 50 Hertz, and we apply some processing that can be just a low-pass filtering stage or some spectral analysis, typically based on discrete Fourier transform. So what can be a PMU? Here it's the example of the PMU we have in our lab. So it's a small box that has current and voltage inputs and that outputs all the packets with the measurement on the Ethernet cable here. And if we open Wireshark, so we look at the stream of the packets, we can see that the PMU is streaming packets that can contain measurements that are the blue line, or control packets, synchronization packets that are the gray lines. So it's quite an easy instrument that can be deployed in all the substation and all the important nodes of the network. But it's the standard that so standard 60255 that has been released in 2018, and as you can see, it does not contain the word phasor measurement unit, but is related to measuring relay protection equipment. So the idea is that the PMU will not be just an instrument for taking measurements, but will take also a control action and will decide whether a line has to be opened or not, whether a line is congested or not. So we are talking about not only an observer, but also an actuator. The IEC standard specifies some methods for measuring what is the synchrophasor, the frequency, and Rokov, but also some compliance requirements, as any other standard. And in particular, in the standard, we have two performance classes that are tailored upon specific application requirements. The M class, that is for measurement application, that is expected to be much more accurate and that accepts higher latency. So we don't need fast measurement, but we need high accuracy. Or the protection class, the P class, where the focus is put on fast responsiveness rather than high accuracy. What are the metrics we want to consider to guarantee the compliance with the standards? There are accuracy metrics. So there is an error on the complex quantity that is called total vector error that tells us what is the error of this complex rotating phasor in terms of amplitude and phase. There is the frequency error and obviously the Rokov error that are quite straightforward. But we have also some metrics related to how fast is our PMU. And in particular, we consider two parameters: the response time, so the time the PMU takes to settle down after a discontinuity, an instantaneous step, or the reporting latency. Because what is important to say is that the PMU will give us some timestamp measurements, so then we can aggregate all the measurements and compare the measurement with the same timestamp. But we have to be sure that the measurement is available at the output of the instrument as fast as possible, because we have seen that the control action have to be taken in the orders of seconds. So we cannot wait the packet too much time. We have to be as fast as possible. These are the requirements, so they are not interesting for us in this context, but I just wanted to give the idea that the PMU normally, in our scenario, will work giving from 10 up to 100 estimates per second. And the latency depends on how fast is the PMU, but if we work at 50 or 100 frames per second, we want for the protection class no more than 20 milliseconds latency. That is not impossible to reach, to achieve, but is quite challenging. Now, this is the standard. This is what measurements want to do. And how do we check this in METAS? So in METAS, we have a PMU calibrator that is more or less organized as in this scheme. So I don't enter in the technical details, but what we do is that we generate the test waveforms as defined in the standards, and we amplify them in terms of voltage and current up to the levels expected on the field. We supply to the PMU under test, then we downscale them by means of voltage transducer and current transducer, and we reacquire them. And on the reacquired waveform, we extrapolate the reference values for synchrophasor, frequency, and Rokov. And then when we know the reference values and we collect the PMU data packets, we can evaluate whether the errors are within the standard limits or not. As you can see, it's a quite complicated system, but this is one picture of the system in the lab, and it consists of an industrial controller like a National Instrument PXI, the amplifier for voltage and current, the transducers, our DUT, that is the PMU I showed you before, and the PC to control all the results. Now, what are the main challenges? So the first thing is to be sure to be able to extract the reference values, and to do that, since the signal that has to be tested is also not only a purely sinusoidal, but represents also dynamic condition, we have to do a nonlinear fit that is quite complicated on the reacquired waveforms, and that does not guarantee perfect convergence, but we made a study to guarantee that in the neighborhood of the reference values, our fit is converging to the optimal minimum of the fit cost function. So we are quite sure that the estimated reference values are correct, but the real problem is that we have a quite challenging target performance. So as any other calibrator, we have to guarantee an accuracy that is at least one order of magnitude than the DOT. And if we look at the standard requires a total vector error in the order of 1%, that if we look, for instance, just at the magnitude error, we are talking about 10,000 ppm. And that is very easy to achieve. The problem is that in the last years, they started to deploy PMUs more and more accurate because they are designed to cope with very challenging condition, and in nominal conditions, so in 50 hertz, in a very stable grid, they are able to guarantee a TV that is 2 orders of magnitude lower than the standard. And so our calibrator should be even 3 orders of magnitude lower. So we would like to be able to guarantee a magnitude error not larger than 10 ppm. And this for voltage and current is quite challenging because we have many uncertainty sources in our system that goes from the purely transforming stage, so with the voltage transformer and the current shunts, the stability of the amplifier we use, the precise synchronization of our system, and the nonlinear fit. But this is the work that is going on. This is an example of a test on our PMU here in the lab. And you can see how we are able to reproduce not only purely nominal condition, but also distorted and dynamic condition. And we are able to provide a calibration report where we check for each channel of the PMU what is the error. Here I'm showing an amplitude step where we check the response time I talked to you before, the delay, and so on. And we can assess the performance of a PMU directly on a very flexible architecture that can allow us to reproduce different test conditions also outside the standard ones. In conclusion, what we want to include also in our infrastructure. So first of all, our PMU calibrator is at the moment synchronized with the GPS antenna, but in our lab, we have a much better time and frequency reference source that is given by the White Rabbit. So the idea is to integrate this infrastructure that is one of the most important benefits of METAS in our system, and also to integrate a calibrator of merging units that is very similar, and PMU and merging units will be the most important actors in this digital substation. So the idea is to merge them in the same system to be able to calibrate both the devices at the same time. So in conclusion of my short talk, what we have seen is that power systems are rapidly evolving towards what we call smart grids, with an ever-increasing penetration of distributed generation and renewable energy sources. But before we get at that point, we need to bridge technological gaps where measurements have a crucial role, because measurements will be the backbone of the entire control system. Since renewables have no rotating inertia, we have to be faster and more accurate. So this is even more challenging. The instrument designed for this kind of problems is the PMU. And here at METAS, we have one of the best PMUs in the world, and we have to improve its performance to finalize and to make it available for the market. And the future steps are to integrate with the work of the other groups of METAS to make it more stable and more reliable. And with this, I thank you very much for your attention, and I'm here to answer your questions.
Guglielmo, thank you very much for this comprehensive and very well explained talk. We now know what PMUs are and what METAS is doing in the domain. We have quite a lot of questions. I would like to start directly with a question from my side. The first one here on the list in the chat How do you explain the slow and attenuated oscillation with a periodicity of several seconds we have seen on slide 8? You know?
So I go back. Yes. Inter-area oscillation that took place in Europe had modulation frequency of 0.13 something hertz, and so it's difficult to define very clearly what is the period of this kind of oscillations because they depend on many factors. One of the main idea is that you have to imagine that our system is like some balls connected by some springs. When you excitate one of the springs, all the other springs will start to oscillate, and the time the power flows from Portugal to Turkey and comes back, so from the two extremes of the network, so we go from the most west part to the most east part of the network, this creates an oscillation. So this 10 seconds corresponds to this kind of reflection of power that is going left and right all over the countries. Then obviously the system is much more complicated than that. This is a very rough approximation of what is going on. But yeah, this is the main idea of what can be an inter-area oscillation. And it's quite astonishing that we can see something that happens on the mountains between France and Spain, even in Ankara or Istanbul.
Okay, thanks for the explanation. I would like to continue with two questions from Marc Olivier. On slide 5, what's the typical voltage at the power plant generator before stepping up the voltage?
So it depends on the type of power plants, because obviously different technologies have different specific transformers before injecting on the lines. But here in Switzerland, the transmission network, so where the generated energy is conveyed before being distributed, we have two possible levels that goes from 380 and 220 kilovolt, and then it's downgraded by many transformation up to what is our 230 volt in the plugs here at METAS. For the power plants, it depends, because we can go from 100 kilovolt to even lower ones based on the specific technology you want to use, because a nuclear power plant is different from an hydropower plant, and it's a matter also of the lines that you are able to put in the specific area, because obviously it depends on the connection. But yeah, the order is on the hundreds of kilovolt.
Okay, so the second part of Marc Olivier's question is about on slide 6, there's a power link between UK, France and Norway, and also between UK and Ireland. He supposes that this is, of course, a submarine link, and hence must be DC.
It's DC and it's single phase.
It's not synchronous with the rest of the continental Europe. That's the question then.
So it's all the islands have specific conditions because of geographical reasons. So the idea is that all our system in the continental part are three-phase, because three-phase guarantees less losses of energy when we transport the energy. But when you have to do a very long cable, and especially if it has to go below the sea, usually we do DC single phase. Since we are DC, as Marc Olivier pointed out, we lose the frequency information. The important part is that in these islands, so the connection between the islands and the mainland is most for mutual assistance. So if UK needs to import more energy, we can send energy, or if we need to import energy from UK, we can, rather than to keep the frequency stable between us and them. Yeah, this is the problem. But since Europe is mostly connected in mainland, this is the idea. Also, Iceland is a completely different topic. So it's there are some occasions. I come from Italy. The typical example is Sardinia, that has a huge undersea line that connects Sardinia to Italy. So yeah, for the islands there is a different condition, but it's more a technological limit rather than a choice.
Okay, so there's a further question from Kai Stelting. He wonders about I would say the economical relevance of installing a smart grid, because in Switzerland he states that blackouts are quite rare, and is it worthwhile to invest all this kind of smart equipment when we have still a nicely managed network in Switzerland?
So this is a very good question, even if it's politically incorrect. No, it's true. So Switzerland is in the best position ever, because Switzerland is, as at its borders, the most important countries of Europe that produce a lot of energy. So in case of necessity, Switzerland can easily import from Germany and France or from Italy. So there is no need. The thing is that the Federal Council, because of political decision, has decided to withdraw from nuclear. And if you lose nuclear, so most of the energy produced in Switzerland is coming from hydro. Hydro is not entirely a green source of energy. It's more a blue source of energy because it's not entirely green. But okay, this is a detail. So the problem is, if the cost of fuel and all the Switzerland is not able to produce energy by itself. Okay, so we have to import either uranium or fuel to make the traditional power plant work. So you need an alternative in case the cost of producing energy becomes too high. The cost of importing gas or fuel and things like that. The most green solution is to include the renewables, but the renewables have some challenges. So the economical investment will be huge and has no direct impact. It is more an investment for the health of the planet. But Kai is right, because the system is very stable, and if you go to Swiss Grid, so our system operator, they would be very happy to keep the system as it is. But the politics have chosen another path, so we have to deal with the decision of the politicians.
Mm-hmm. This brings me to another question of, I can link the question of Kai to the question of Christian Wüttrich, or the comment more of Christian. He's not fully agreeing with you that green electricity implies less stability, because he argues that we have water turbines in Switzerland, and that this blue energy is also a green and stable energy. And you mentioned before that it's a blue energy. What do you mean with that? Can you comment on Christian's comment?
Yeah, no, it's true. So Switzerland is currently relying a lot on hydro. And hydro, especially in Switzerland, is one of the biggest dams in Europe. Let me show. So this is one of the main hydro facilities all over the continent, I think also all over the world. So it's true. We have hydro, and hydro is quite stable. And hydro is, especially in Switzerland, we use these pumps to store the energy. So all the energy that is produced in excess by the dam is used to repump the water up, like a kind of storage of energy, because we use the energy to produce new energy in the future. But hydro, we know that the water will be a problem in the future years. And so, again, it's more an investment for the future. Hydro is quite stable, but still relies on turbines. Okay, so you have water passing through turbines. You have a kind of inertia in these turbines because even if you stop the water flowing through the turbines, they will not stop immediately. Mm-hmm. Instead, if you take the example of solar energy, if like today there is no sun because of the clouds, you have no control on the clouds. So this is the challenge of less stability and less inertia in the renewables. Instead, hydro is in the midpoint between a thermal or a nuclear power plant and the traditional one. But water will become a resource in the future, so maybe we will not be able to waste somehow the water to produce energy because we will need water for other reasons. But these are all strategical decisions that have to be taken. Switzerland for sure is not on the brink of a crisis. It's more the trend of all the world, especially here in Europe, to withdraw from nuclear, and this requires to find alternative solution. We cannot be dependent on the cost of gas because we are not able to produce gas, and this is the idea of the Energy 2050 plan.
Of course, this is also then impacting the carbon dioxide output. But this brings me to another question which was asked in the beginning also of your talk. Do you think that we have to reconsider nuclear power to have a stable electricity provision in Switzerland and to have a stable network? Or is the smart grid and renewables, green renewables sufficient to have a safe provision of energy?
So nuclear is one of the most optimized kind of power plants. And if you ask to me as an electrical engineer, it's a pity that we withdraw from nuclear because it has a huge potential. So it can produce a lot of energy. It can produce, it's very easy to control, but then we know what are the environmental problems related with a nuclear power plant. Let's not talk about the disasters. Okay, these are obviously unfortunate events that we don't want to face, but also the management of old nuclear power plants that are abandoned. So power plants where we have to deal with the radiation issues and so on. A previous METAS event was dedicated to that. It's not an issue, but if you decide that nuclear energy, because of the waste, because of the CO2, is no more a solution, unfortunately, you have to find alternatives. From the electrical point of view, it's one of the best sources we have. And until we have uranium, is for sure also one of the most stable and easier to control. So nuclear is a very powerful solution. And I come from, I think, maybe the single country in Europe. So Italy is one of the very few countries that has no nuclear power plants because of a referendum after Chernobyl accident. And for Italy, this is a huge cost because Italy has to import gas from Russia, and this has a huge impact on the economy of the country.
So we'll see how this develops in Europe, worldwide. This is interesting to see. I would like to continue on a question, interesting one from Johannes Hoffmann. He would like to know whether the network could be attacked with PMUs supplied with a wrong GPS signal, which will lead to another phase. This could destabilize the network.
Spoofing, yes. Spoofing is so it's part of the cyber attacks you can do on the network.
Yeah.
So as for anyone who has a Tesla, we can spoof the GPS of the Tesla and make the Tesla go in the wrong direction. The same can be done with the PMU. So if you change the time reference of the PMU, you will get wrong results, obviously, and you will take wrong control actions. So this is quite challenging. It's a challenge from the technological point of view. And in the US, already happened in some grids that there was this kind of cyber attacks. So cybersecurity is a big problem in the deployment of a smart grid. If you consider what we have now, at home you have just a counter, no, probably in the basement of your building, and BKV or whatever is the operator where you live passes and controls. So there is a very centralized control, and the data they are transmitting are just for marketing reasons, so to decide how much you have to pay. If instead this information becomes to be crucial to decide whether to open a line or not, this data becomes very, very important and very, very to be secured. And in fact, when I was at NIST, there was an entire part of the department that was just for cybersecurity, because there is a lot of issues related with the GPS, with the privacy of the data we are transmitting. So it's a big problem, but it's more from the informatic and legal metrology point of view.
Exactly, also interesting for us. Another question is, do you consider remote calibration of PMUs deployed in the network, or have the PMUs come to METAS to be calibrated?
So for calibration, there is, I think you can do remote calibration periodically. At least what I've seen at NIST is the IC Center for PMU calibration. And what they do is that before deploying on the field, a device among the set of the devices is calibrated in the lab with all the tests. And then they do some periodical checks. So obviously you cannot reproduce all the tests on the field, but you can do some statistical analysis. Now, I don't know the rules because this is quite an important decision, because if the PMU becomes like a counter, there are the same problems of calibrating the counters on the field. So it's a decision that can affect the stability of the grid. But technologically, yes, because it's just a matter of accessing the network where the packets are. So it's not a big issue from the technological point of view. From the legal point of view, it's a matter for lawyers.
Okay, there's the last question. Then you have done it, Guglielmo. It's from Peter Hurliman asking why not use the renewable energy sources which cannot be planned to load e-cars, electric cars, boilers, and so on at home. Is that not interesting to maintain the stability of the network?
So electric vehicles is a huge topic. I don't know why, but in Europe it's not so important, but in the US it is. So the idea is that if we look at this example here, so the electric vehicle, like the Tesla, can be seen as a battery that is moving around the network, okay? So you can store some of the energy in your car, and then with your car you go to Geneva, and then you plug the car in Geneva. So you have a kind of battery that is moving around the network. And this is absolutely a new way of storing and transporting energy. And you share the transportation with the transportation of staff, of humans. So it's absolutely one of the solution. But in Europe, it's not so well deployed. I think also because electric cars in Europe are not so frequent. Now they are increasing very rapidly. And here in Switzerland, we have many. We have also many charging stations. So absolutely, yes. It's just that the storage capability of a car is limited. Okay, so obviously. But for very small microgrids, like a small quartier, this can be definitely a solution. Yeah.
Okay, thank you, Guglielmo, for all these answers. I would like to ask you if you can make available your slides. I think it's will be possible. We'll put them on the intranet, I think, and I would like to make a bit of marketing for the next seminar, which is on the 7th of April, and it will be Florian Stucker speaking about a new infrastructure built up in METAS Sense Lab about characterizing motion sensors. So looking forward to this seminar. Thank you once again, Guillermo, for this very nice
Thank you all for the attention.
Talk. So have a good day. Goodbye. Thank you.